Hello everybody, we'll talk today about bio-inspired materials, dynamic thermal comfort, and all-weather materials. So how do humans adapt to temperature variations? Well, temperature control, thermoregulation is a part of a homeostatic mechanism that keeps the organism at an optimum operating temperature, since temperature affects the rate of chemical reactions inside the human body. The stimulus for thermoregulatory behavior, such as seeking shade or adjusting the thermal insulation of our clothing, is the conscious sensation of thermal discomfort. Vasoconstriction and vasodilation help humans preserve the core body temperature through sweating and shivering, respectively. However, one size does not fit all. Different people have different temperatures at which they feel comfortable, since besides the thermal, the personal variation, the basal metabolic rate is different for groups of people from different climate zones. The mechanisms that humans use to exchange heat with the outside environment are radiation, and that radiation represents the majority of the dominant mechanism of heat exchange in sedentary activities. So radiation, evaporation is very important, especially when we're doing the sport activities, outdoor activities, and also conduction and convection. The rate of heat exchange with the outside environment is determined by the metabolic energy production of specific for each type of activity. Now, what was the source for our bio-inspired design for new non-composite materials for thermal comfort? Well, we have the dynamic, fascinating dynamic light reflecting skin of the mirror spider, as can we see here in the upper row, this is an excellent source of inspiration for next generation adaptive thermal management systems. The silvery patches that you can see on the abdomen of the spiders look like some solid pieces of mirror glued to the spider's back. However, these patches can change size depending on how threatened the spider feels. These reflective patches are composed of guanine, which is used by the spiders to change color. This highly evolved natural architecture allows for the patches to be dynamically switched by muscle cells contracted and expanded in contracted and expanded states, and thereby they modulate the local coloration and change the reflection of light through the skin of the spiders. Humans have developed since the 1960s the space blanket, as can be seen in the middle row. This is a static technology that can either reflect all instant light when it's on, put on the skin, or reflects nothing if it's taken off. However, we wanted to develop similar with the spiders. We wanted to develop a wearable material that can dynamically change the amount of incoming light and infrared radiation reflected. So basically, we want to develop a platform that gives us the excellent ability to reflect heat, which is specific to the space blanket, but combine this also with the capability to dynamically change the amount of heat dissipated, similarly to how spiders change their color. So how can we do this? We use a stretchable support fabric and textile adhesives to build such a platform They can then be integrated in normal everyday clothing. So what are the steps of preparation and testing of nanocomposite materials with such properties? So first of all, we have the deposition of a nanometer thick metal layer, followed by the deposition of a thin elastomer film by spin coating or thick coating, and then thermal aging on a hot plate of the elastomer film, followed by delamination from the substrate, and then we analyze the nanocomposite materials in terms of spectroscopic properties and mechanical properties and the surface roughness and scanning electron microscopy. Test the capability of the materials for thermal regulation. We mounted the nanocomposite materials in a custom design holder that allowed for application of strain on a sweating hot guard plate. And we tested the thermoregulatory functionality under control condition in the initial state without mechanical actuation and then with mechanical actuation. So this test confirmed the tunable infrared properties of composites, and we then evaluated the performance for adaptive thermal management for wearable configuration, and we measured for experimental measurements, and we modeled the heat transfer between human skin, the nanocomposite material, and the surrounding environment for different states of activation, mechanical activation of the material. So, in terms of the amount of the heat flow regulation by mechanical activation, in the initial unstretched state, the nanocomposite material maintains a steady heat flux from the hot plate with an average value of about 250 watts per square meter. As we mechanically activate the nanocomposite material, the steady state heat flux from the hot plate increases up to about 310 watts per square meter for mechanical strain of 50%. So basically, these measurements demonstrated that the nanocomposites manage up to 70% of the metabolic heat generation, which is about 75 watts per square meter for resting individuals or sedentary individuals at office. Additionally, the nanocomposites need an estimated input of about 3 watts per square meter for mechanical actuation switching. The nanocomposites do not consume continuously power, making their energy requirements substantially lower than all other active thermal management platforms. So, these materials, in their initial relaxed unstretched state, feature set point temperature of about 14.5 degrees Celsius, similar to the one for example spaceflight, which is static platform that does not have the capability to dynamically change the amount of infrared radiation reflected or transmitted. As we strain the material, the nanocomposite material, the set point temperature increases. So, for example, for a strain value of 50%, the set point temperature is about 20.9 degrees Celsius, which is similar to that of wool. And at a greater strain, around 100% mechanical strain, the composites feature a set point of 22.7 degrees Celsius, which is similar to that. So these experiments and calculations confirm that nanocomposites can be adaptively and rapidly actuated with strain to maintain a person thermal comfort across environmental set point temperature range of 8.2 degrees Celsius, which is one of the largest dynamic ranges reported by any for any comparative material for thermal comfort, such as the textile materials. So, in essence, the nanocomposites possess excellent switching capabilities, wherein their infrared properties can be modulated in real time to mimic a broad variety of fabrics and textiles. Finally, I want to mention an added benefit of these materials. It is the added benefit of energy savings. Basically, these energy savings are the result of an expanded band of temperature that's regulated in buildings both for heating and cooling. And this can lead to overall to approximately 3% energy savings globally if such materials would be used at commercial scale. Thank you very much. Thank you for your attention.